first is Professor Huang from Peking University, Beijing, and he's going to talk on this title here. Thank you.
Thank you. Thank you for introduction, and I'm very happy to be here. And so as you can see, there are actually two topics. The first topic is about machine learning for Wiener-Hopf factorization, and this work is conducted by the first one, Xun Huang. He is my PhD. And the second topic is for aeroengine noise radiation, conducted by another one, Mr. Wang Ruichen. He is also here. So basically, these two topics are conducted by two of my PhD students, and I'm Xun Huang. And so I'm going to I'm going to focus on the introduction and the motivation why we want to do this, and then very briefly introduce the details. And for more information, you can refer to my students for more details. And also, I would like to spend like 5 minutes to introduce the oncoming Wiener-Hopf workshop at Hangzhou, China. And first, very brief introduction of my Peking University. It's also a Peking is the traditional pronunciation of Beijing. So it's also Beijing University, and this is our campus. And my school is an engineering school, so it's somewhere over here. But I want to point out that here is the mathematics department, and also this roof is for visitors in their mathematics departments. So if you are interested to visit Peking University, you'd better contact the mathematics department rather than my department. And my group is acoustic laboratory, and we do some computation. The top left one is our own solver, DES solver for some turbulence-ingested rotor noise applications. And my group also conducted some experiment work, and so middle one. And the right one is today's topic about the modeling of aircraft engine noise. And so previously we have done some work for aircraft engine. So it's a duct acoustic modeling. We try to apply Wiener-Hopf. And the problem here is special is we consider special is we apply some kind of osmosis splits over there. So there are 3 rigid splits. And so by studying this, basically we do some Fourier expansion in theta direction, and then we can get the Wiener-Hopf equation here. But sadly, the kernel is a matrix kernel, and we have like a constant C matrix, and another one is a classical kernel, but diagonal kernel for duct acoustics. So we actually don't know how to factorize this matrix. So we have in this paper we have to do some approximation. We approximate this one by this one. Right, and this mu mn is the actual wave number. So by doing this approximation is just supported by numerical results. Looks like this approximation also works well, but we still want to find some kind of exact solution, right? So we need to factorize this one, and then we think about how to solve this problem, because this matrix is very large and it's not non-diagonal. So we think about how about apply the machine learning method to factorize this one. So this is one work we have conducted in past 3 years. And another one is this one. So this is a cylindrical duct noise radiation problem. And the Wiener-Hopf model it's very early. It's 1977, proposed by Mount. And then Ranscher extended from Eindhoven, extended this method to some duct with arbitrary and varying cross section, but still cylindrical. And then Gabab and Asli from Southampton, they include a center body in this model. And this is their numerical setup. So actually, in their model, this center body is infinitary from left to right. And then the next important work, is from Peek here, Cambridge, and he extended the previous work to some kind of finite length center body, either outside or inside. And then the next one is again the Higgs group, some kind of S duct. And our previous work is trying to apply some splits over the right half side. And but all this works, this cross section is cylindrical shape. And but recently we start to think about this question. This kind of aircraft engine shape, so its shape clearly this is not a cylinder shape, and we want to approximate this one by some kind of elliptic shape. So how to resolve the noise radiation problems from this elliptic shape duct? And so I'm going to first introduce this one very quickly. And so basically the left one is the sketch of the problem, and the right one is the schematic of the model setup. So basically this is, we just approximate the duct as some kind of elliptic shape and half infinity. And here we need to consider some kind of, it should be a virtual vortex sheet, because actually in our current work, the background flow is uniform. So there is no shear flow, there's no vortex sheet. But because but if we want to set up the model, we need some kind of vortex sheet to enable us to establish the boundary conditions. And here is the definition of the coordinates. And then the governing equation starts from the convective wave equation. And the special part is this one. In the elliptical coordinates, we are going to split two sets of Marshall equations. So in classical cylindrical coordinates, this one is Bézier function. Here this one, Bézier equation, and here change it to Marshall equation. And another special thing for this problem is this condition. In cylinder case, there is only one orange point, but currently for elliptical case, we have a focal line. So we define these two conditions for this focal line. So this is another specialized condition, I think, only for this case. Then we just split the whole acoustic potential to two parts. One part is incident part, another part is a scattering part. We use subscript S and I to denote them. And the incident part is a classical solution, and with different modes. And this is a dispersion relation. And then we just this is the boundary conditions. So we need to use this. We need to use this across this virtual vortex sheet. So there's a particle displacement, and defined by these two equations. And if later on, we are also considering for shear the flow. So then these two terms, the Mach number should be different, but currently they are the same. And also here is a wall boundary condition, and this is a pressure continuity across this virtual vortex sheet. And then we define the half range, the Fourier transform, and we define this G plus, and then we decompose everything. All these manipulations are very similar to the classical operations in duct acoustic problem setups. So I don't want to. I just skip all this. And then in the end we got this the matrix equations to Wiener-Hopf equations, and luckily this kernel actually is a matrix, but this kernel is a diagonal kernel. So it's very easy to factorize it. And then we also discuss the numerical behavior of the whole entire function. So I just skip all this. And here is after getting the model, we also compare to numerical results. And the left one is the finite element simulation setup. And here, so this is the elliptical duct and PML boundary conditions to absorb sound radiations. And you can see that at different cross sections, so this direction and another direction, the third direction, and also for two different cases at different Mach numbers. And all these comparisons are similarly quite good. And also the left one is instantaneous pressure field, and the most left one, this is from the model, and this two is from the numerical results. And you can see, and also this is SPL results, and this is numerical results. The difference, only difference here, because this one is from PML, the sound wave has been absorbed. So just very quickly to finish my introduction of our work in elliptic shaped engine. And the next one is machine learning. And so before jumping to this, we have some kind of, we have learned the so-called PIN, right, physics informed. Then we start to think about physics informed, basically is impose a constraint by Navier-Stokes equations, right? So can we impose a constraint of Cauchy-Riemann equations? So we introduced this two equations as a constraint into the neural networks. And the good thing is then we can apply the automatic differentiation to conduct all this by using neural network, so-called automatic differentiation. There's no truncation error, and it's very easy to implement. But of course, it's difficult to converge. And here is our neural network, the whole architecture. So the left hand, the top left is the architecture of the neural network. So it's actually not difficult. It's a classical deep neural network, and there's no special feature for that part. And the input is the coordinates of the whole complex coordinates, and the output is going to be the positive part of the factorized matrix. And we didn't produce both G plus and G minus automatically. We only approximate G plus, and the G minus is going to be computed by this equation. And there are differential is going to be obtained by neural network automatically, and the constraint is here. So this is the whole architecture. And so but before applying this technique to architecture to a very complicated problem like our ductal acoustic problem, we first consider some simple problem. So we first consider this two no staggering parallel plate scattering model, and there's an incident wave. I believe everybody is very familiar to this one, so I don't want to go through all these details. But I do want to emphasize here is this is the boundary condition part. So you can see there's four U1, U2, V1, V2. They are already known, right? And they are also boundary conditions. So we are also going to use this in our constraint as well. So that So then we, in our network, we need to learn, and we define some loss functions. And initially, we just define this Cauchy-Riemann loss, and then we found that it's actually not so easy to converge to find the solution, even for such a simple problem. And then we find out we also discussed with Anastasia, and Anastasia suggests us to also consider this Cauchy integral loss. So we introduce the second loss function to make sure that this one will ensure the analyticity with Cauchy integral. And then the further one is we also found that the boundary condition is also very, very important, right? So we also included this one in our loss function. So then in the end, we have three loss functions, each corresponding to boundary condition, the Cauchy integral, and also the Cauchy-Riemann equations. And then we define the matrix to examine the performance. And so there are two matrices we have used here. One is far field directivity, and originally we only used that one, the far field directivity, to examine the performance of the network. But then it turns out we found that that one is not enough. So we also then we introduced another one, the second one, the MSE. And the reason I'm going to show you in the next, in the results. But then we do some so-called ablation experiments. This is common. This is a common practice in neural networks. So basically, we introduced a lot of different themes in this machine learning black box. Then we just try to remove something, ablation something, and to examine how about the performance changes, right, with respect to the ablation of all these different things. So basically, we set up the weights for different loss functions. And initially, we set all these loss functions. We use all these constraints, and we get MSE and the far field and the near field results. You can see the loss function is so large. And then if we just set 1 to 0, and this one is for Cauchy-Riemann, and this one is for the integral parts, and this one is for the boundary condition. So if we set 1 to 0, then we can see, right? So then we can see that it's actually very important, right? Because when we set this Cauchy-Riemann constraint to 0, that means we didn't consider this in our neural network training. And then this error becomes very large. And if we change this one, set this one to 0, it looks still okay, right? So that means this integral parts looks not so important compared to another two loss functions. And for boundary condition, it's also very important. You can see here, right? And also you can see here, right? And the reason, let's have a look. So this is the far field directivity. And this one is very, very large, only at certain angles. So if we only introduce this metric, and then that means our neural network is going to be biased only at certain angles. And then if we also introduce the near field solutions, then we can get better results. So that's the reason why we need two metrics. Also, you can see the difference, right, between the exact one and the analytical one. And so basically, let me just very brief. I just very briefly introduced our idea, right? So the first work is the mathematics-informed neural network, and currently we only consider the guiding example, and we show how to introduce the constraint due to Cauchy-Riemann equations, and also we have shown that not only this one, right? We also need to consider other issues like boundary conditions as well. And this work has already been published recently, but it's still ongoing, right? And the next step, we want to introduce the exponential terms. So then the next problem is going to be the staggered parallel plates. And we currently are studying Professor Abraham's method, and we try to combine our neural network method to resolve that problem. And so this is our first part. And the second part is elliptic shaped. So actually, I always told my students to do as many literature review as possible, because I think this problem is not so difficult to resolve, and I don't know why nobody looks like have considered this problem previously. And also, this problem is very important for future aircraft engine applications. So if someone happen to know that somebody else already conducted this, please let me know, right? And but otherwise, if nobody has done this, so then we are very happy, because that means we already resolved the problem at like 1977 months work. Then we can extend all the following works, like including liner and including the center body, so on and so forth, right? Also all for this problem. And also any collaboration is also welcome. And next one, because I just very quickly I go through all this part because I want to spend some time to do some advertisement about the oncoming workshop at Hangzhou, China. And yes, basically I think it's actually it was quite difficult for Gennady and also Natasha. They have spent a lot of time to prepare a proposal 2 times, right? Twice. And the first time is because of due to the pandemic, so have to be cancelled, and I have to apply the money again, and also we want to encourage everybody submit your intention to attend this workshop as soon as possible. Then it can help us to finalize the final program. And someone may have concern, right? You may have never heard about what is Hangzhou, the host city. Hangzhou is the most popular city in China, right? So for tourists, right? And here this is Hangzhou's view, and I found that there's a promotion video prepared by the city. So I want to bother everybody, and I just show you this video. watching video for Asian game, so you can see there's a lot of sports elements. And as I said, that Gennady and Tasha have conducted a lot of works. And from now on, I'm happy to step in and do more help. For example, what I can see is, for example, if you need a visa, right, and if you need an invitation letter, for example, if you not only want to go to there, you also want to visit Beijing or somewhere else, and you need an invitation letter, I will be happy. Just send me an email. I will happy to prepare that for you. And there are other issues. All these issues, if you have questions, just feel free to ask me. I'm still here, and but I have to leave tomorrow because from this Friday is our national the Science Foundation review starts from this Friday. I have to fly back and take some panel meeting. And but my student is also here, so you can also ask him. And some of my students are going to be volunteer for this workshop later this year. So should be we will do our best to help everybody, and hope you have a wonderful journey to China as well. And feel free to ask our everything. Right? That's all.
Thank you very much. Fantastic. So you've covered a lot of ground. I'm sure there's lots of questions. John, do you want to come in?
Yes, please. In your method where you're doing optimization and you simply regard the equations of motion as constraints, that is arisen in many other problems, and a common method is simply to introduce Lagrange multipliers. So all you do is you multiply each equation by the Lagrange multiplier. And of course you have to find that as part of solving the solution. But that method has been used to brilliant effect in other branches of continuous mechanics. And I was wondering, is your method different from that? Essentially different? And is there mileage for a different approach here?
It's a very good question. And we didn't consider that way, the Lagrange multiply. And we just do this way. The reason is actually for coding, right? Yeah. When we apply machine learning, and in this way, it's better for us to incorporate the idea into this way. Yeah. And we didn't consider how to implement Lagrange multiplier to this setup. But that's a good try.
A lot of JFM papers.
Yes, yeah, all right. But we
people
didn't.
In Cambridge
we didn't
for a living based.
Yeah. But related to the elliptical, cylindrical, semi-infinite waveguide. So, John, you never did it for non-circular cylinder in high frequency?
No, but Nigel Peake had a research student who certainly did this problem with a flatter base. Yeah. And he did a lot of ray theory.
Yeah.
And
so,
you can see
but
the rays
they didn't use Wiener-Hopf method.
Yeah.
Use some kind of double KB.
So, that's correct.
Yeah. So in high frequency, you can get the directivity pattern pretty well for this problem, which would be good to check your students'
compared
results
to
against that. I think you would be. Other questions? Sure.
I might miss something at the beginning, but you mentioned about necessity or to factorize constant matrix plus diagonal matrix. In the so the kernel is C plus K. Image theory method is required. So how you do it?
This C is a constant. We know this one.
What?
And this one is a constant matrix. C is a constant matrix.
Constant C plus K is not constant but diagonal, yes?
This one is diagonal. K is diagonal. C is a constant matrix. And the factorization for this one is known. So K plus K minus, because it's diagonal, it's very easy to get. And then we just get this equation.
So you construct explicitly factorization for this matrix, correct?
C plus, you mean there's a direct results for this one?
Yeah, so the K is diagonal, so obviously you can factorize that.
Well, okay, of course, but the sum, the C plus K.
The sum you can't factorize.
Huh?
No.
No, we cannot.
Okay, this is what I wanted to
we cannot factorize that. So that's why we approximate.
Yeah. So you're using your machine learning method.
Trying to solve this problem later on. Currently, we're still 2 times 2, very small matrix.
Sure. So I'm sure people, we have run out of time, I'm afraid. So I'm sure everyone will be interested in asking you questions, not only about your talk, but also your excellent promotional video and Gennady and Anastasia, you're going to be promoting this trip.
Yes, it will be promoted even further. But the most important, not the most, but one important point. Remember, its workshop is in China, but it's under auspicious in Banff, so it's not Chinese workshop. So if you have issues with the countries now, because it's not easy time to time to have permission to go to China, you would not go to China, you go to workshop organized by American Institute in Banff Institute, simply replaces in China. Okay, thank you.
So it's Canadian, not American.
What's the difference?
Okay, let's move on. We're eating into Elena's time, so thank you again.